Hello, Maxime.
Hello, hello.
So today this webinar will be a follow-up of the one we hosted in November with Victor. And so this one was focused on advanced sensors for inline PV inspection. And I will give the floor to Maxime, who will present you the sensor we use on the Platform Zero project.
Thank you, Susie. I will share my screen now. Okay. Well, and I will start presentation. Do you see my screen? It's okay.
Yes, it's perfect.
Okay. So, as you know, this is we are inside the Platform Zero project, the project that is based on the development of process monitoring for achieving zero defect manufacturers in the PV industries. So inside this project, we are organizing several webinars, a series of webinars about different topics. Here you can see the list of all the webinars, and today is the second webinar that is focused on the advanced sensors for inline PV inspection. So uh, just brief introduction about who I am and where I'm coming from. So I'm working in IREC, Catalonia Institute for Energy Research, as a leader of the Materials and Device Characterization Group. And inside the Platform Zero project, I'm leading the work package 2. And my main background is in the characterization or advanced characterization of the materials, mainly for the photovoltaic applications. But in the recent years, I'm focused a lot on the developing new tools, new methodologies, new systems for the implementation in the industrial environment for the monitoring the industrial processes. So adapting the laboratory systems um, to the industrial environments. And my talk today will be focused in four main axes. I will start with a brief motivation on why do we need to include the advanced sensors in the production lines. Then I will speak a bit about the nomenclature of what do we really mean by this advanced sensor term. And I will tell you about the main limitations, or let's say main requirements, which appears when you start developing sensors for the inline integration in the industrial processes. And I will give you some examples of the sensors that we already have developed inside the Platform Zero project. So let's start with the motivation. Um, of course, the nowadays the materials and electronic devices that are developed by different type of materials, different type of devices are super complex. They consist of different materials, of the combination of materials, and they are very prone to some small deviations. So you need to have a very fine tolerance when you are developing new devices or producing new devices and high tech devices. And of course they are using high value materials, and sometimes the processes are very energy intensive. So in order to give you a bit more idea on how this can be and what can be the complexness of an production process. Here you see some steps that are needed in order to produce thin film photovoltaic devices. That is a main focus in the Platform Zero project. Here you see different machines, different steps, different treatments that need to be made during the production process. Here in some typical PV devices, thin film PV devices, you have around 7 processes, and then you have hundreds of controllable and maybe even more uncontrollable parameters that are changing during the um, that might be changed during the production process. And finally, when you are producing a device, you get up in having this quite complex or structure of the device that consists of several layers. The layers are of micrometric or sometimes even nanometric thicknesses, and then each layer has its own um, uh, its own property. It should be and its own parameters, and everything should be very well respected in order to get up to the highest efficient possible devices. And of course, there is then interfaces between these layers that have also quite a strict influence on the devices and on the parameters of the devices. So this is what we obtain as a result of these complex processes of following different steps. And as a result, of course, we get some dispersion in the final efficiency of our devices. And in sometimes this dispersion is even so high that we need to really throw out half of our products. So this is really, really complex, and this requires a lot of not only the material but also energy, and also the um, the forces from the personnel. And one of the solutions that we are proposing inside the Platform Zero project in order to reduce this dispersion and avoid as much as possible this dispersion in the final products is to introduce the monitoring processes in each production step, or introduce as much monitoring parameters as possible in each production step. And this is our motivation. So we have the problem of inhomogeneities in stabilities between the processes and inside different processes. So, and this is what is our motivation in introducing some advanced sensors in the production step in order to monitor them as better as possible. So let's speak now about the nomenclature. What do we mean by this advanced sensor term? So of course, if we are speaking about the simple sensor, this is a typical devices that respond to some physical inputs of the environment. It can be light sensor, heat, temperature, pressure, whatever sensors we have around or in nowadays. And the main objective or the main target of these sensors is to make a bridge between the physical world, so these environmental conditions, with the digital realm. So to transfer the environmental um, uh, conditions in the language that is can be worked in the digital phase. So in some signals, in some electrical signals that are already afterwards can be treated by the PCs, and then this is already where we are collecting the information and then process the information, when we can give not only the information about the past but also predict some information. So there is a lot of models that do this way. So this is a typical sensor that we can really meet in our day-by-day life. But by what do we mean by advanced sensors? If we are thinking about another another topic of the material science, so then the advanced sensors will be will bring this bridge between the digital realm, the same, and some physical properties of the materials that composing our devices or our structures that we are aimed to analyze. So this would be quite it's this explanation of the advanced sensors would give you a bit of the idea. So you have some device that can transfer the measurable properties of the materials in some signals that are clear by the digital devices, by the also by the PCs, by the computers. And as example, very easy example, it can be some X-ray fluorescence gun. Probably some of you use it or you know about the existence of this type of guns that based on the X-ray fluorescence effect, and that these guns can measure the chemical composition of the different type of materials that you can use. All this can be a simple multimeter that really measure the electrical properties of the of the materials. So the main difference maybe between the typical sensors that we meet in our day life and advanced sensors would be the working concept. So if in typical sensors, they are just detecting or they are reacting in some way on the um, environment that they are analyzing, then the advanced sensors in most of the cases would provoke some reaction of the material. So we have some incident signal, so we have something that generates the reaction in the material, and then we're measuring this reaction on what happens with the material. So we have this scattered signal, and then based on these results of this scattering signal, analyzing this scattering signal, we can understand the properties of the material. So this is in main terms, this can be understandable as a working concept of the advanced sensors. So going a bit in the technical part, in the details of what can be the main parts of the advanced sensors, these as based on the working concept, of course, this some excitation source that sends this incident signal. So in this can be some electromagnetic waves or particles or acoustic waves or some even internal chemical or biological processes inside our materials, inside our samples, that start generating some reaction inside the material that we are detecting. Then we have some probe heads. So these are the parts of the sensor that directly um, interacts with our samples or directly interacts with the materials by sending this incident signal and then collecting the scattered signal. And they can be of a different type. They can be superficial or immersion, depending on the application, depending on the type of the sensors, and they can be contactless with a collimated or focus beam or whatever. So there is a really huge combination on how these probe heads can look in on. And then, of course, we have this scattered signal is detectors that detect the reaction of the material of our sample with the incident signal. It can be some electrical, it can measure some electrical signals, some magnetic signals, optical, spectroscopic, or whatever. So this is also quite there is also quite big variety of different type of detectors. So, and of course, uh, we need some unit that controls the sensor and collects the data in order to process this afterwards. So these are this, even it's not maybe the main part or the critical, most critical part of the sensor, but it's always should be present this control and data processing unit that collects the data, that controls different parts of the sensor and so on. So in order to give you a bit more example of what we can name this advanced sensor and what is the uh, typical how this typically can be used in our labs usually, or in the industry even. So here you can see that the typical Raman spectroscopy system. And if we are dividing in these three parts that I showed you previously, so we can see that the excitation source for this Raman spectroscopy system will be a laser, so a narrow band light that is typically used for the Raman spectroscopy. Then as a probe head will be this big microscope with different features, with different tools, allowing to illuminate the sample, allowing to change the objectives and so on, and including some specific filters needed for the Raman spectroscopy. So it's very complex tool, but still the main objective of this microscope is to bring the excitation light to the sample and then to collect the signal. So this would be our part of the probe head of this complex sensor. And then we have the detector, which typically in the Raman spectroscopy is some monochromator with connected CCD camera. So we have some dispersive element, and then we have a camera that detects the different signals at different wavelengths. So like this, we can easily bring all this complex system that has different parts, different elements. We can bring this complex system to a very strict and very easy explainable system. So we have three main parts, and then of course, as I said, we always have this control and data processing unit that in this case would be some simple PC that shows us the data and allows to make the measurements. And of course, in order to show the data correctly, we need some uh, uh, control and data processing software. So the development of the sensors is not only the hardware part, it's always should be taken account the software part, which sometimes is more complicated to develop than the hardware part. So with this one, more or less we are now understanding what do we mean by these advanced sensors. And let's now speak a bit about some limitations or requirements that need to be taken account when we are developing sensors for the inline integration. So, okay, here I put the list of different limitations or different requirements from the industry that we got so far while developing different projects, different sensors for different producers. But of course, this list can be increased much more and can be much longer. And I will tell you just details about few of these limitations. One of them is the accuracy and precision. Let's imagine that we have some process, and we are in order to control the quality of this process, we are measuring the Raman spectra in this specific step of our material that is produced in this step. And we know that the deviation in the Raman signal is quite tiny between different materials, between different samples, but still even these deviations are quite tiny. They result in a huge deviation in the final performance of the devices. So we need to be sure that our sensor can detect these tiny deviations in the Raman spectra. So we need to provide the correct accuracy and correct precision, or correct signal to noise ratio in this case, to be that the deviations in the samples to be detectable by the sensor. So this is one of the critical limitation that is required when you're developing the sensor. Another limitation is measurement time. So when we are speaking about the measurements in the lab, we have not limited time, so we can do it during hours, minutes, days sometime, and this is okay. This is we are not we don't have any limitation. However, when you are going to the production line, you have some specific timing for each production process, and then if one of the production processes like here presented results in a product every 5 minutes, so this step is finished every 5 minutes, and every 5 minutes we're getting new sample from this process. uh, that means that our sensing station or our sensors should take not more than 5 minutes in order to analyze or inspect the sample and to provide the answer if the product is good or not good. So we have this limitation of 5 minutes. Of course, 5 minutes I take just to very roughly. Sometimes it can be seconds or even milliseconds. So depending on the production process, these time restrictions can be really hard to meet. Uh, another Another limitation that can we should take in account while developing the sensors is the fast response. It's also related to the timings. It's also related to how fast we are getting information from our sensor. So here you can see an example that imagine we have a different sensors that are installed in different production process steps, and they are analyzing different properties, and then we have really a big matrix of correlations between the properties of the materials and between the changes in the signal of each of the sensors. So we can get really huge amount of information, and then, as I said, every 5 minutes we're receiving this information, which ends up to the hundreds and hundreds of data that should be fastly analyzed, and we should directly give a response to the production line if the product is okay or not okay, if it passed the quality or it didn't pass. So that's why sometimes we need to limit the information to very relevant information, to the most accurate correlations that really provides us details, or really provides us valuable information in order to say if the product is okay or not okay. In the last year, so yeah, we was involved a lot in using artificial intelligence in order to process the data from the sensors, and this is what we was developing quite intense in our lab, and also in the framework of the Platform Zero project. And here you can see and as example, one of the publication we recently published, just last year, we published an methodology that allows to fastly um, um, detect some inconsistencies or some deviations in the signal that is provided by different sensors. And also here we can make in a bit deeper analysis of this data, and then we can extract some physical information of not only about that something happened within the production process, but also what happened really inside this production process, and what changes or variations happened in our samples. And the next limitation or the next requirement is, of course, related to the maintenance and calibration. Here, I would show you some example that of the some version of the first developments of the sensors that we was making inside one of the European projects. So here you can see that when we got the first version of the sensor, we have installed it, and then in 70 days, by checking the signal that we are receiving from this sensor, we see there is a really huge shift in the position of the bands. And this created the problem not only in that this shift appeared and the signal changed and something happened with the sensor, but it's also um, it's also um, forced us to change the models that were needed in order to analyze the signal from the sensor. So we had to readjust all the calculations, all the analysis of this data from this specific sensor. So the easiest part or the more correct part was then to make another version of the sensor that becomes more robust, more stable, and do not requires these high maintenance inputs in order to recalculate the models for the data processing. So then the second version of our sensor already was stable. We have measured this in 100 days, and you see that there is no any shift of the peak. So we don't need to provide any so we are sure that our sensor is stable during this time of 3 months or even more. So this is what is related to the maintenance and calibration that should provide the correct reliability and reproducibility of the sensor signal. So we should be sure that the signal we are receiving is really related to our samples, to our materials, and not is the problem with the sensor. And of course, this is what is always question when you are going to the industry is the price. So when we are speaking about some laboratory systems that are very versatile, can do very nice and good measurements in the long term, and these systems are very good, but their prices are sometimes is huge, or in many times it's really huge. Like, yeah, here you see the typical Raman system, very nice Raman system, but the price is 300,000 euro or even more. But then by removing this versatility of the system, because this is not maybe always needed to the industry, because they have very fixed product, they have very fixed production line, and they have very fixed processes that they need to control. So you don't need a system or a sensor that can monitor 20 type of different materials if this production line is producing only one type of the material. So you need to focus on this one type of the materials. You need to focus on the signal that is produced by this type of materials, and then this allows to really optimize the sensor, to speed up the measurements, and also strongly decrease the price of the sensors that can be installed in line in the production process. So the price is very critical, and we should always take in account that this how to decrease this price in order to be more interesting for the industry to implement these sensors. And with this, I will coming to the final part of my presentation. It's examples of the advanced sensor that we have developed inside the Platform Zero project. So as I said already, I showed you this image with the different production steps, and then when looking on these production steps or on the sample that we're receiving on each step, we got up that we have really a lot of different properties that are critical to be monitored at this different production step. So you can see that there is a really uh, different type of properties that we would like to monitor, or we need to monitor in order to get the full picture about the production process, to get the full control of the production process. And then in order to satisfy this requirement, or to measure all these properties of the materials layers, we identified several techniques that looks to be interesting in order to get this information about the layer properties, but also techniques that can be really easy, or acceptably easy to adapt in terms of the sensors, and can be used as the sensors. So and here you see some example of these techniques. And while taking in account all these techniques, we have developed a set of different multi-sensors, or sensors that implement different techniques. And if I'm not wrong, inside the project we finally developed around 30 different sensors, um, uh, with different configuration, adapted to different production lines, to different production processes. And the way we was developing the sensors is, we start with a laboratory testing. So we had a set of samples from the different production lines, and we start, of course, with our laboratory equipment, trying to measure, to trying to identify which of the technique is really sensitive to these variations inside the production process. And then uh, we was thinking a lot on how to optimize these laboratory systems, to make them compact and industry friendly, in order to install inside the industrial production processes. So we spent quite a lot of time in order to identify the optimal elements that allow to to make the sensors more compact, more robust, more stable, but really focused on the needs of the specific production processes. And then in several cases, we was thinking, okay, we have the set of independent sensors. Why not try to merge them in one multi-sensor? So here, in these conditions, we are multiplexing the sensors, so we are minimizing the measurement time, because in these conditions we already can measure the same area of the sample in parallel, in the same time, by different techniques. And then we are also can, some part of the sensors that in these conditions can be reused by different techniques. So we are minimizing the price, we are minimizing the number of components that we need in order to make the multi-sensor. And currently we are on the process of integration of these multi-sensors inside one advanced sensor stations that we called here inside the project. This is advanced sensor station, that this station um, that implements different sensors. So this contains different sensors and can be used for different production steps. And the next step for us will be to install this advanced sensor station directly inside the production lines, to see and then to implement and to see the effect of our sensor on the production process directly. Okay, going to the examples, as I promised, I will show you the examples of the sensors. And one of the first sensor that I can show you is a spectroscopic multi-sensor that contains three different techniques that can measure quasi-simultaneously in the same spot of the sample, Raman spectra, photoluminescence, and normal reflectance. And these type of sensors can be adapted depending on the needs of the samples or the production process. So we can change the excitation wavelengths for the Raman spectroscopy in order to excitate the correct Raman modes or the correct materials in the that we need it for the production step. And then we can, in the case of photoluminescence and the reflectance, we can select this different spectral range to be analyzed, so we can work in the near ultraviolet and visible range, or near infrared range, or in both ranges if it's needed. So we can extend to the full range from the near ultraviolet to the near infrared. So it's also quite relevant when we are changing from different materials, different layers, and different production steps. So it's depending on all these factors. We need to select the correct excitation wavelengths and to select the correct spectral range in order to monitor the signal from the samples. And how we are integrating these spectroscopic multisensors, as you show in the previous image. There was a probe head, is a separately part of the sensor that is connected with the optical fibers with the components, and this components box, can be really far from the probe head. So we have specific space of the components cabinet where we are placing all the components related to the excitation and collection of the light. So we are quite flexible in how to integrate the sensors in the production process. And here you see some short video on how this sensor is working. There is nothing fancy on here. It's just illumination of the some spot of the sample, and then we're collecting the information in this spot, and moving the sample below the sensor. We can collect different points. We can have a matrix of the properties from that are measured by the sensor. So we are collecting more information from the sensors. And then, as you see here also in the picture, there is possibility to install several sensors in the row, several probe heads in the row, and we can analyze in parallel different properties of the sample. So we are increasing the speed of the analysis by measuring directly several spots in the sample. The next sensor is a LIPS sensor that you can see here is very easy integrable together with the Raman sensor. So you can see here, this is how it can be integrated. And here you see the photo. And what is the LIPS sensor? This is a laser-induced breakdown spectroscopy, and it's used for chemical composition estimation. And here you can see some short video on how the sensor works. So when the sample arrive to the behind the sensor, now it will happen. Yes, now. So when the sensor arrive behind the sample, we start excitating the signal with a laser. So there is some excitation of the laser, and then we are detecting the emission lines from these materials. So we are detecting directly different elements that are constituted of our layer. And this is also quite flexible in terms of we can adapt it to different spectral ranges. So it means that we can detect different elements depending on which kind of samples or which kind of materials we need to analyze in different production steps. And one more example of the sensor is the imaging sensor that we call it imaging sensor, but it's based on the hyperspectral um, imaging. So we're illuminating our sample with different wavelengths. In our case, we use four of them: blue, green, red, and then white is a broad white light. And then we're detecting the image of the surface of the sample, and this provides quite a lot of information about the morphology of the sensor or of the sample, and also about the sometimes changes in the composition of the sample directly can be visually seen. So this is a sensor that directly sees some variations in this aspect of appearance of the sample or sample surface. So we can directly detect if something happened went wrong during the production process. So this, and here also this sensor contains two different type of camera, one for the micro, another for the macro scanning. So this means that we are scanning the sample in both macro scale, so in terms of centimeters, square centimeters. So we're detecting the big range of the sample, and then we are also scanning the sample in micro scale, in the range of tens of micros or hundreds of micros. So we're detecting some really small, tiny variations in the surface of the sample, or appearing some inhomogeneities, some cracks, some pinholes on the sample that are really critical afterwards to the quality of the final product. And finally, I will show you the PL imaging sensor. So this is also quite known technique to be used for the photovoltaic materials. So we know that a good photovoltaic material or good photovoltaic absorber should have a good PL signal. So when you're having the huge samples, it's nice to measure directly a big surface of the sample in order to define any possible inhomogeneities in the sample while producing. So we are not only comparing different samples from different production runs, but we can also detect if the sample produced now is really homogeneous enough, and it's inside this criteria of good homogeneity for the sample. So here, as you see, we're eliminating a big spot on the sample surface, and then we're collecting the information about the luminescence intensity from all this surface. And the same as in the previous case, we can adapt this sensor to different spectral ranges depending on the type of the material we are analyzing, and we are using. So with this, I would end up my presentation. I thank you for the attention, and thanks, of course, to the Platform Zero project that is organizing these webinars. And I'm ready to answer your questions if there are any.
Thank you very much, Maxime. I just wanted to add a quick compliment to this webinar. So so lately, like shortly, we released a bunch of videos on all the sensors that are used in the Platform Zero project, which you can check on our YouTube channel. So don't hesitate to go on the Platform Zero YouTube channel, and you have a series of video about each sensors with additional explanation to what Maxim just told you.